Okay, welcome everybody. Let's get started. So thanks for coming today. You've chosen the data visualization class over fancy desserts. If you're in a school of computing, you've probably heard about this big announcement that is happening right now. I don't have desserts, but I can tell you what it is. And so the School of Computing has a naming donor. So basically the Kaler Foundation is sponsoring $15 million. And the School of Computing will be renamed as the Kaler School of Computing. So that's the big announcement. That will be an endowment. So that means we don't have $15 million to spend next year, unfortunately. And it's going to come in pieces, but essentially that will mean that there's going to be, better support programs for undergraduates, also possibly more fellowships for PhD students, and all these kinds of activities, right? It's going to be student focused and early career faculty focused. So, yeah. I don't think that it will be lower tuition, unfortunately. Yeah. And it's been very hush hush, and I've only heard about it a week ago or 2 weeks ago, right? So, yeah. But if you go back right after class, you might still get some of the desserts or the swag. Cool. So to the topic at hand, last time we ended with this design critique. And so maybe take a minute now and refocus a little bit, think about what you talked about in your group, and then we'll discuss it together. Okay, so let's talk about this. The first question we always ask is, what are the marks and channels? What's the mark here? Exactly. And the channel is? Position, color. Yeah, exactly. So we have kind of the shape or position of the kind of the top of the surface and the color. So what is kind of the thing that I always talk about when we talk about visualizations is I usually say don't use any unjustified 3D, right? And so what do you all think about the use of 3D here? Yeah, so if I want to paraphrase you, you were saying that interaction makes it easier to perceive the surface, make it easier to perceive the different parts?
It's not immediately clear why the rates for various input loans. I don't think that's super obvious. But there's already there from as well.
I missed the one word in there,
the yield.
Yeah.
It's percent yield per year of
yes.
Government bonds, and it's not entirely clear to me, particularly without domain experience, why you need to see the yield.
Okay. Well, that's a good question. So maybe we haven't talked about the data. What is the data that is shown in here?
Annual yield of treasury bonds.
Exactly. So the yield of treasury bonds, and so treasury bonds essentially pay out a yield, and it depends on what's the maturity of that bond, right? So if you buy a bond that matures in 6 months, you will get that money in 6 months. If you buy a bond that matures in 30 years, you will get that money in 30 years, right? And so obviously interest is going to be different between a short-term bond and a long-term bond. And so what would we expect? Which one would be more volatile, short-term or long-term bonds? Short-term, exactly. And so we can kind of see that, right? We see that the front of the curve here is much more volatile than the back of the curve, right? So it's a little hard to see, but we can see that the back here is way less up and down than the front of the curve, right? So that's kind of the data here. And like, I guess not everybody has to know what this data means, but it's kind of interesting. And so what are some interesting, like, can anybody guess what happened here? Yeah. The recession happened, the government needed money, so we had these like very high short-term yields. But it's actually, is it the recession? Because it so yeah, they were lending a lot of money, giving people or like they're paying high interest rate on the money, and then eventually crashed. So it looks like actually the 08 recession really took the bottom out of the interest, right? Okay, so any other questions about the data and about what's going on here before we move on to the visualization? Yeah.
Maybe like a comment plus a question. So like they've got along you kind of got it hidden, but like the different terms for the bonds along the side there.
Yep.
Like two extremes when you look at it from the side are like really easy to kind of see compare. But like in the middle, all the rest kind of just get obscured. I was wondering if this would be more effective to just plot the 30-year and like 1 year or 1 month to show that comparison as opposed to doing all that stuff in the middle.
Yeah, I think that's a good question. So maybe to repeat the comment is like we can see the first, like the short one, the 1 month treasury bonds and the 30-year treasury bonds reasonably well, but everything in between isn't so easy to see, right? And so why don't we just plot those two lines, right? I think that's a reasonable question. I guess we can look at, is there any time in history where we see some kind of like inconsistent behavior? And I would say that it looks like sometimes, right? So for example, here it was fairly stable. And then here we have in like, that in 2011 or so, we have like this bump, which isn't really as pronounced in any other area, right? So I get what you mean. And I think the most, it's, if you want to take the principal components of this plot, it would probably just be the 1 month and the 30 months. But there might be a little bit more nuance in there.
Something I noticed around 01, there's like before then, the data, like you put it to the side, you will see it more easily. I don't know if that's when those type of bonds started being sold, or there's no data for them before.
That is a good point. I'm guessing that they started selling the bonds there.
I have a question about the data.
Sure.
So on the, I guess, C axis where we have 1 month to 30 years.
Yeah.
Do we have the data between like each step? Like, is there data for 1.5 months, or are they just drawing a line?
I think this is discrete, right? These are different products that you can buy. There is no 1.5 month government yield, like a government bond, right? So this is like basically an interpolation, and I guess we can question whether this is reasonable, right? Because it's definitely not a linear scale. It's like 1 month to 30 years, right? There's like a massive difference between those two. I still think because they are kind of like temporally ordered, that maybe plotting it like this isn't terrible, but you would have to kind of like, I think, you have to think about this, and you have to kind of like, you shouldn't, make any financial decisions. And I guess this isn't really what this chart is about. But, it is a little bit tricky. I think it's a bit of a weakness of the design. Yes. Yeah.
In addition to the volatility over time, the distinct difference in the last 10 years has been that the slope of the yield per turn is decidedly different than it has been historically.
Exactly. So we have a very different slope. So it's it used to be more consistent between short and long term, and it's now very inconsistent, right? And so that's kind of an interesting observation.
If you wanted to make something like this, would you use D3, or is there standard rules?
You cannot do this in D3. Well, never say you can't, but it would be really hard, right? This would be much easier with a tool like WebGL, where you like a computer graphics kind of tool, right? Where you render a surface, where you have all of this camera information, camera navigation, and so on. So yeah, D3 would not be the tool of choice for this. Probably the first visualization that we've critiqued where that is actually the case. But that's kind of like where, whenever you have like and it's mostly because of SVG, right? SVG doesn't have the concept of a camera and an object in the scene graph, and like lighting, and so all of this doesn't exist in SVG. And so you really like, since SVG is really like what you mostly use in D3, that's kind of like where this comes from. Okay, so let's go back to the 3D, because I think we've been talking about it a little bit. 3D, good or bad? Why?
For me, if this is a static image, it would be awful because the depth perception just doesn't help. But the fact that you can rotate it, I think that's a huge plus. It makes the 3D work.
This is a very good observation, right? 3D things are, we need to move them around. And we do this also in the real world, right? If you want to understand a 3D object, we move around it and then we get different perspectives on it, or we move the object in our hands. And so that's definitely true, right? Like your printout isn't going to be all that useful. And I don't actually remember whether the print version of this or not. But it is much more evocative, much more interesting. And you can see all of the nuance with 3D, and so with interaction. And so that's also like one of the weaknesses of 3D is that we have occlusion, right? If I put this chart like this, I don't see what's going on behind here, right? But by allowing me to navigate, I can kind of like reveal this information piece by piece. Any other comments on 3D? Yeah.
I think the use of the color gradient and the white lines for each kind of year, different type of models.
Yes. So the color gradient is a redundant encoding here, right? So we have the height of that point on the surface is also redundantly encoded by the darkness of the color, which we can very easily see when interest or yield was very high back in the 90s. It's very dark, right? And in the 2014 to 18 or so, it is very light because it's also very low. Yeah.
Because the color is almost the same, so in that section, the horizontal lines are the same.
Yes, so we have a bit of a contrast issue here with these supporting lines, right? So, if that could be like a smart improvement that you take into consideration what is for the line segment, what is the color of the surface, and you could kind of dynamically change to a darker color. That would be possible.
This is the question. So the one month, they made it black, and then everything else, they made white. Like, what would be the purpose besides like pop out?
Yeah, good question. I think it's like, I'm sure they tried black support lines, and I'm guessing it looked too much like a wireframe and too little like a surface, right? That is just my guess. I can't, unfortunately, just play around with this here, but that's probably it. And I think that the top line graph here is pretty interesting, and this is why it's black and high contrast is what I would say. Yeah.
I just feel like maybe color gradient that they show for the doctor in that section of the laptop. It's because like when we see from the right side, we cannot really see the height, but the color helps us understand. If instead of a gradient, if it were a solid color, when you turn it like this way, then it will just look like a flat color.
Yeah, so I guess if I paraphrase you, what you're seeing is that the color gradient also re-emphasizes a little bit the ridges, and it looks maybe like a little bit you would see on a geographical map where you also have shading depending on elevation, right? So what do you think about the navigation? Notice that this is not unrestrained navigation, right? I can't actually zoom or pan. I can actually, well, this is just my browser, my operating system, but the tool doesn't let me zoom in. It also doesn't let me pan. All it lets me do is rotate. Why do you think that is?
Too much freedom to be about it.
Exactly. So here, restrained in the degrees of freedom for the navigation allows you to kind of like, there is no way, like I can never lose this, right? There's like if I had freedom to pan around, I could kind of like get into some weird state. And this is after all like a newspaper, right? So you don't want people who Like they don't have to know about how to navigate in this tool. It should be completely intuitive. And so that's why it's this constraint, like this, why they use this constraint navigation. Any comments on the labeling?
Just a moment ago, 6 months was entirely removed. And that, you know, isn't necessarily a conceptual problem with visualization, but nevertheless.
So what you're saying is that the labels are not always ideal, and so we can definitely see here, for example, that we have occlusion, right, going on. I don't like, and they can also hide behind this white piece here. But what's interesting about those labels?
You also say that those angles, you won't be able to use that data anyway.
Yes, exactly. So yes, if I look at it from the front, right, I can't see the nuance anyways, or maybe I can, but.
I just noticed the, well, X, Y, the Y with like the 1 month, 3 month, 6 month, it's not like consistent scale.
Yep, it's a nonlinear scale here. But you know, one of the problems about 3D labels in 3D is also that it can be tricky to read labels. And what they're doing here, you know, let's just imagine I had a fixed set of labels that is always parallel to the curve up here. And if I rotate this, it would be very easy to not see it, right? If the text would be actually a 3D object that moved with the chart, it would be fairly tricky to see. And so what they're using here is a technique that's called billboarding. And so they always make sure that the text, even though the object rotates, the text is always parallel to the screen, right? And so that kind of like keeps it visible, keeps it readable, no matter how I turn it, right? So that's like a very like neat thing, which we also, of course, know from computer games, right? That text is usually billboarded. Okay, so what about the storytelling aspect here? So, you know, I have this narration here. Anything that, well, do you find it interesting about that, or? Yeah.
When I was playing around with it, I thought it was helpful to be able to like quick snap to the different angles to get it lined up right.
Yes.
At least that would make it easier to kind of view it.
Yeah, and so it's kind of like a pretty interesting thing, right? Because here somebody has thought about like what would be some interesting pieces for you to look at in this chart. They put it in the right place, they put it in the right direction, but they also provide additional information, right? They provide a little bit of a story here, right? And this is something that maybe you should also strive for in your projects. Like, you know, we would like you to like not just give us a visualization that we're supposed to explore, but that you have analyzed the data and tell us a story about the data. And so here we have the story deep in the valley, right? Basically, there's no yield and short-term bonds, but there's this little outlier here where Congress threatens to let the country default, and suddenly the yield goes up a little bit, right? So that's kind of like interesting, and you wouldn't know that, right, unless you do some research on what's going on, what happened at that date, and so on. And then you can here essentially here there's kind of an interesting inversion that they're pointing at, right? So you have short-term bonds that have higher yield than long-term bonds. So that's also something that you mightn't have noticed, right? So the story really like helps here. And then if you, now we're kind of like taking away the 3D completely, right? Now they've perfectly aligned it so that we actually see a 2D plot. And so this is kind of a good moment to revisit what's better, the 2D plot or the 3D plot here. Like, this is the same data. You think this is way better?
Yeah. Easier for me to look at.
Yeah.
It's hard to see like that lining up with it to get when they're comparing.
Yeah. So here you see that crossing, right? So that's kind of interesting. Yeah.
I almost, I do like this one more, but I almost think like it kind of confuses me sometimes when I try to look at it from scratch again, because I guess I'm tuned to think about that space between the bars is almost like an error bar, or like the standard deviation of the curve, which isn't true. It's more like, but it is a measure of spread of some kind. So I'm wondering if you were to either rename it or have a different unit to indicate spread of some kind, that this would tell the same story better.
Yeah, I guess one piece of information that's lost in this chart is the the different angles that we talked about earlier, right? So this is good to tell us the difference between the min and the max yield, but it's not necessarily good to like understand the to understand kind of like the change in steepness of the slope here, right? So that's kind of like the thing where I think the 3D is actually, this is the easier chart to make, and this is the one that is maybe like from an analytical point of view. Maybe you want to show the 1 month, 10-year, 30-year highlighted here, right on top of this. Then it would be pretty informative chart. I still think the 3D has something going for it, right? Just because the visceral nature of it, and seeing it in that way, and seeing the surface. And usually I'm also always very skeptical about 3D aspects, but here's like the other 2D version of this, where it's a heat map, right? And it's the same data, you can see it, but it's just like less tangible in some sense, right? I don't know how to express it. Maybe this is also a personal opinion. Anybody have a thought on this chart compared to the 3D one? Yeah.
Originally, like, because of the gradient and is like double encoded with the height, it's originally it's like you could just make the graph just like this and you don't even need the 3D, but it is a lot harder to compare the extremes at the same time. Like, it's really difficult to see what is happening at a specific year along all the way.
Yeah, so we see this a little bit, less precise maybe. Okay, and then if we keep going here, we're now suddenly in a different country, right? And so here we have negative yields. And here they've made this interesting choice of using color, a different color, which, why does a different color make sense here? Because it's negative. So if we translate it into like color scale terms, we have a diverging color scale because we have a meaningful neutral point, right? And so we want to show things that are below zero in a different color than the ones that are above zero. Recall, for example, I showed you this plot of Florida that didn't actually consider like the zero sea level, 0 meters or 0 whatever feet elevation. And that just didn't look like anything, right? But if you plot that chart where you have a divergent color map at exactly the level of the ocean, then you can suddenly recognize the Florida or the coast. And this is the same here, right? It would be tricky, especially in the 3D chart, to see that this is actually negative, which is kind of like a weird development, right? Fiscally speaking. And then we finally have this kind of like this comparison to Japan, right? And so, overall, good visualization, bad visualization, do you like it? Lots of thumbs up. So this really made a bit of a splash in the Viz community back when it was built. And there are a few critiques here, and there's also an interview here with Gregor Aish, who is the person who built this, or with some other people. But I think the first link here is an interview with him, and they were like he's talking about his design process. And the other 2 links here are critiques of that visualization. And kind of like the consensus of like the people who were critiquing it back then was that 3D is really tricky to do, but this is like a good case of using a 3D visualization, right? Because it's so specific, so narrow, and it avoids many of the pitfalls of 3D visualizations. Okay, any other comments before we move on? Yeah.
Something like to be able to improve that chart would be when you're navigating like from the categories of the bonds, trace that line.
Yes.
Going, so it would be easier to see.
That would be a cool extension, right? So that I can click a particular like 10-year bonds, and I would see that line pop out. Yeah, I agree. Cool. So, contrary to what, like if you downloaded the slides already from the website, I shifted this a little bit around because we have two more topics. Recall we were talking about tabular data, and we looked at this classification from the Financial Times chart, and we looked at things like magnitude, right, and then change over time. And then we looked at some diverging charts and part of a whole relationship. And two topics that are still open that we want to explore today are correlation and ranking. And originally I was going to do ranking next, but I switched it around because I have another ranking exercise, and I figured we'll just do like a little bit of lecture and then have a break by doing this exercise afterwards. Otherwise, we would be just going straight into discussion again. So let's talk about correlation, which is kind of like one of the key tasks that we want to understand about tabular data. So what is correlation? It's basically the question of how do two or more variables behave relative to each other, right? Do they kind of like linearly correlate, as you can see here in this extreme case where we have what's called a correlation coefficient of 1 or an R² value, or is there no correlation, like in this example here? Or is there a negative correlation, right? Like in these examples here. So these are kind of like, what you would kind of expect from normally distributed data. If you have some correlation, you would see something noisy like this, right? And then of course, correlation isn't doesn't have to be just linear. It can be of arbitrary complexity. We could have like whatever, some squared correlation or so, but we could also have these weirder patterns, right? And if you just wanted to look at linear correlation, probably just a statistical description is going to be okay, right? But typically, visualization really shines if you have these interesting patterns where you combine correlation patterns with outliers, or you have something else going on in the charts. And so how we visualize correlations, well, what I'm showing you here is a scatter plot, right? And so a scatter plot is obviously a great tool to visualize correlation, but you can also do it differently. So the scatter plot, and especially for higher dimensional data, we're not talking about 2D tables here, but higher dimensional tables. So we have the scatter plot matrix, and another common technique that you can use for this is parallel coordinates. And so we'll be diving into those two. Here is like a comparison of those for a table of scores of certain students in the subjects math, physics, dance, and drama. And you can see, let's look at the orange one, right? So if you look at the table, this person has high scores in physics, low scores in drama. And so we can kind of look at what is physics versus drama here. So it seems like this person is a little bit similar to this other person, right? And if we want to look at the same person in the parallel coordinates chart, we would just trace it across the different dimensions. So we can kind of see this person's profile across the axis, maybe a little bit more easily, but therefore, at the same time, it might be a little bit harder to see patterns between pairs of axes in a parallel coordinates compared to scatter plot matrix. But let's dive into scatter plots first. So scatter plots is when you have two orthogonal axes visualizing one dimension each. And the questions is really like, how do you encode the mark and how would you deal with many points? And then, of course, for the mark, you can also choose, well, the mark shape, and then you can choose additional visual variables such as the size and the color, and so on. Well, many points is also a big issue. So one thing that you can do with many points is that you can use transparency, right? So that you can, for example, if you give your points 0.3 transparency, then you might not see the individual points so much, but you will see over plotted areas kind of like suddenly get very dark, right? So you can kind of distinguish between dense and looser regions. But similarly, if you have a lot of points, you can also think about some other approaches like binning and doing hex bin plots, for example, or heat maps, right, instead of scatter plots directly. That depends a little bit on how much data you have and what your tasks are. The thing that you often want to also think about if you analyze correlation with scatter plot is like you're trying to do some regression, and you can either draw a regression line, but there's actually studies that show that we are regression machines, right? We can spot whether there is a regression, and we can very accurately identify regression lines in scatter plots, right? So drawing a regression line can be helpful, but it's not necessarily super important because people can just do this. And as so often, XKCD has good advice. I don't trust linear regression when it's harder to guess the direction of the correlation from the scatter plot than to find new constellations in it, right? So definitely keep an eye out for that, right? So even if there is like a statistical, like statistically speaking, there is a trend here, it is just a little bit too weak to be reasonable. And then also recall Anscombe's quartet that I showed, I think, in the very first lecture, which is this kind of data set that has, statistically speaking, the identical mean, the identical variance, the identical median for all of these data points, or for all of these 4 data sets, but in practice, and they also have the same regression line. In practice, they look completely different, of course. So the scatter plot matrix is kind of like the big brother of the scatter plot. And so it's a matrix of size d by d, where d is the size of the dimension. And each row or column is 1 dimension. And each cell plots a scatter plot of 2 dimensions. And so here is like an interactive example that we looked at before, right? When we looked at brushing. So we have this is the iris data set, the machine learning data set. Zoom out a bit. And so we see the sepal lengths, sepal widths, petal lengths, and petal width. And so basically what this means, this row here is petal width, and this column here is petal width, right? And here we're plotting, in this chart here, we're plotting petal width against petal length. What's the relationship of this cell here to this cell here? They're mirror images of each other, right? So like everything above and below the diagonal is the same, just flipped over, right? And sometimes you could make an argument that it might make sense to just not even draw that. Maybe you, like what I've once played with is taking this space here to show like an enlarged version of one of the scatter plots. But in practice, on our rectangular screens, it's often just useful to do the whole thing, and then you can also trace it a little bit more easily. And the other thing that is obvious in here is that the scatter plots in the diagonal are not all that helpful, right? They show us a little bit of a distribution. We can spot that there is a gap in here, right? But maybe what would be better here is if we show a KDE plot or a histogram here instead of a scatter plot. So we have kind of like a hybrid thing between a scatter plot matrix and a histogram. And in fact, this is like a very common visualization. For example, if you use a tool like Seaborn in Python, this will be like one of the standard plots they have. And scatter plots matrices have some kind of limited scalability. So because it's like, you square the dimensions, you're really like done pretty soon. You can't do like a 500 dimensional data set with scatter plot matrices. So you're roughly limited to 20 dimensions. And maybe 500 do 1,000 records. If you have more records than that, you have to think about something else in terms of like, how do you bin, how do you aggregate? And especially the matrices, the cells tend to get small. Brushing is important because unlike for parallel coordinates, right, we can't trace, we don't know what this point here is in any of the other charts, right? So that's a problem. So it's good for looking at trends, but it's also hard to understand how does one set of points behave over different dimensions. And this is like, as I mentioned, is often combined with a focus and context technique, and I'll have a video of this a little bit later. For all of these techniques for correlation and for tabular data, we often can like make them like more usable by combining some of this with algorithmic approaches, right? So for example, the previous thing here showed a category in color, right? But if I don't have that category, I can also do a clustering on the data, and I can color the clusters, right, in the scatter plot matrix. So that would be kind of like helping you reinforce and find some relationships between the different data points. Or I can choose, like if I have too many dimensions, there might be some boring dimensions, right? So I could like algorithmically choose the dimensions that have high variance. Or I could choose the order in which to show them. So these would all be techniques that you could apply to make scatter plot matrices more usable. Here is like an example that uses this approach that I mentioned about binning. And so this is actually like here. Well, let's go big. we're showing 1 million data points, right? Each of these cells is rendering 1 million data points now. It's not really rendering it, but it's the binning behind the 1 million data points. And, you know, it's blazingly fast. And this is like a paper about this data aggregation technique. And as you can see, this is clearly like, you know, splatting and aggregation that's happening here. But it is a pretty cool thing, right? That basically tells you, you can handle a lot of data, even with D3, if you just think a little bit about your design and about your algorithms behind it, right? So if you're interested, this is the Datavor project. And then here's like an example of a focus and context navigation. I'm going to play this video here.
The scatterdice application is a prototype implementation of our scatterplot matrix. Scatterdice consists of 4 main components: a scatterplot matrix, a curving layer control box, and a navigation bar. The main scatterplot visualization shows the current position in the scatterplot matrix. In other words, 2 of the dimensions in the dataset. A set of simple navigation techniques allows for controlling the position in the scatterplot matrix. The keyboard of the navigation bar can be used for stepping one position in the matrix at a time. Movement is performed as an animated 3D transition from one scatterplot to another, where one dimension remains constant. The user can also scratch the current position in the matrix to see the animated transition from one dimension to the next. To move directly from one part of the scatterplot matrix to another, it is also possible to perform a hyperjump. If the user wants to see the intervening positions, the path planning interaction transitions automatically from one position to another. Finally, path drawing allows the user to draw the path to traverse on the surface of the scatterplot matrix. Scatterdice allows the user to build queries using the query layer box and a lasso tool, and then see how the query is distributed in other plots. The user can move an eccentric label lens on the plot to see the nominal names of the data points. This also works with query select.
So there's a few things going on here, right? The basics is this, like, you know, you have your scatterplot matrix and you navigate by doing this like 3D transitions, right? Which is kind of cool, but seems more like a fancy gimmick, right? And the path planning and so on, again, probably is pretty cool, but it's in practice really like this paper is now 15 years old, right? And nobody really has ever used this. But there's a few really nice things in here. For example, the use of these lassos, right, and how they're persistent and how they show up in all of these other ones and how they're represented with how they are represented across with these polygons. And then I also really like these kind of smart lenses, right? The tooltips that show you like information about many of the points that you have in here. But yeah, overall, this was like a seminal paper. Of course, you know, academic research always pushes the boundary, and the most important contributions of this thing now are probably widely used, but the 3D piece hasn't been used so much, right? So I think that this idea of having like a small thumbnail-based overview plus the big one, that's kind of like the lasting idea of this particular paper. Okay, any questions about scatterplot matrices? Great. So then next we'll talk about parallel coordinates. And so we've intuitively talked about them a couple of times. They're not all that hard to read, which makes them also good. And I just want to say that parallel coordinates are a bit of a issue, a little bit like pie charts. The Viz community is divided about them, right? Some people hate them with a passion, and some people think they're cool. And I'm somewhere in between. I think they're good for certain use cases, and I would definitely, like, you know, if the right project comes along, I would use them. They tend to be a little bit tricky to read sometimes. So let's look what they're all about. Let me hit this. Okay, so in parallel coordinates, the axes here represent an attribute. So in a scatter plot, we would have like an x and a y, but in that are orthogonal to each other. In x and y, they're parallel to each other. And this is like, by the way, this technique was developed by Alfred Inselberg, and actually not for data visualization, but for looking at high-dimensional mathematical shapes, right? So if you have a 5D shape, how can you draw that? And this has solution to that was this parallel coordinates. But I think they've kind of like have more impact on data visualization than for looking at high-dimensional geometry. And so if we have 2 points, A and B, they would be plotted like this in the scatter plot. And in the in a parallel coordinate plot, we would kind of like find the point where A intersects with the x-axis, find the point where A intersects with the y-axis, and then draw a line connecting them, right? And so what we can see here quickly is that if A and B over X and Y are kind of like behave in the opposite direction, we get this crossing, right? But if they both behave the same way, we would have parallel lines. So that's kind of like an important thing to notice in terms of the patterns. And so each axis here represents the dimension. The lines show the represent the records. And the one thing that's nice about this is that it's suitable for all tabular data types. So you can also show categorical data with it, though it's not perfect. And it's suitable for heterogeneous data. So in the end, this is a line chart, right? A glorified line chart. But the difference is that each axis here is different. It's not just, if you go back to our heartbeat example, for the line chart, we wouldn't have to have additional axes. But if we have something like cars here, then it does make a lot of sense to have different axes, and we can see these relationships. And so what we can see here is, for example, if we just look at this, weight and acceleration seem to be inversely correlated for cars, right? Because we have this kind of like extreme crossing pattern in here. So the heavier a car is, the slower its acceleration, which of course makes a lot of sense. But displacement and horsepower seem to be positively correlated, right? So we see that there's there's a few outliers, but mostly these lines are straight or go up, right? So that makes sense. And so, as I mentioned a few times already when we talked about interaction, interaction is crucial to understand patterns. Like it's easy to understand patterns between two axes in parallel coordinates, but higher, like between multiple axes, is a little bit trickier. And so what I have to do is I brush here, and then I say, let's look at all the cars with a displacement of 350 to about 400, and then we can analyze how do they behave across these other dimensions. Yeah. So that's the easy part to read, but if you don't have interaction. So yes, this is one of the weaknesses of parallel coordinates, right? That it focuses mostly on the correlation between adjacent axes. You can get around this by either by letting people reorder it, and I'll show this a little bit later, but I think the most important mechanism is by interaction, right? So here, if I look at this here, low displacement cars have good fuel economy, and they have bad acceleration, right? So that's something that we can judge, even though it's not neighboring, but because we're using this highlighting here. So interaction can solve this problem a little bit. One thing that I also wanted to show, notice that we have some kind of ordinal data in here, like the number of cylinders is a discrete number, right? There's no 8.2 cylinders. And that works, but it's not perfect, right? Basically, everything there's no 4.5 cylinder cars. We have basically 4, 6, or 8 cylinders in this data set, right? And if this is a standard parallel coordinates plot, this all comes together in this one little point, right? And so it's kind of tricky to trace these lines through these one little points. And you have the same thing here for years. So these are parallel coordinates work best for discrete colors, for continuous dimensions. For discrete dimensions, they're less ideal just because it's a little bit easier to trace trends if you have these continuous data points. And we'll talk maybe a little bit about some of the mitigations for that. This is a parallel coordinates plot of 500 axes. It's not particularly useful, right? So there's a limit to scalability. This was a visualization that I built myself. And I'll show you an alternative later. And this is actually the very first implementation I ever implemented in 2007 or so. What you can see here is not much, right? And so what's going on here is because we have for each data point we have like a very long polyline. There's a lot of ink on this. And so it's not very, like, there's not really a lot of patterns visible. But fortunately, we can do the same trick as we did for scatter plots. If we have overplotting, we can do a little bit of transparency, right? If we make these lines slightly transparent, we can immediately see some patterns here. And actually, this data is random, right? So the patterns that you see here is you know, just the random noise that you would expect. And that's kind of like also a little bit of a shortcoming of a parallel coordinates plot. If you go from a very low to a very high point, you get a long line that graph visually long, right? But it's actually not meaningful that it's long. But yeah, that's just one of the problems. Another thing that you can do is bundling and clustering. But the most powerful thing to do also for scatter plots is sampling, right? Random sampling is an extremely powerful method and very, very simple, right? If you need to visualize 100,000 points and you don't have hours and hours to spend on some scalable visualization approach, just sample it down to 1,000, right? The patterns are going to be the same if you use a good random sampling algorithm. And so, as we mentioned earlier, correlations can really only be seen without brushing between adjacent axes. One solution, as I mentioned, is brushing. The other one is let users change the order, right? So I can drag the axis around if I want to. In a detailed level, there is a little bit of a few problems with parallel coordinates. So for example, we have the line ambiguity if points cross exactly at the same point, which is kind of like the problem with ordinal or discrete data, right? So here in this example, if line A comes in here, we don't know whether this is line A or this is line B, right? We can't know. It's not we just, you know, there's no way unless we change something about the visual encoding here. Similarly, a more complex case here, we don't know anymore which line is which, right? And one thing, the obvious solution is, of course, brushing and highlighting. The other solution would be curves, right? So that you don't use polylines, but use curves. Then you kind of remove that ambiguity. Of course, that has other disadvantages, not the least that it's kind of like a little bit more difficult to implement. And of course, also takes more rendering effort. And then I guess, is it really so important to see the particular line without interacting? That's the other question. So in summary, parallel coordinates show primary relationships between adjacent axes. They work up to 50 dimensions and about 1 to 5,000 records. It's very important to use transparent lines, basically with completely opaque lines. You will have cluttering immediately. Interaction is crucial. Axis reordering, brushing, and filtering are important ones. And they're actually, I didn't show that, but they're actually very good as a 1D filtering, right? So you can create a threshold, only the cars with 4 or more or with 6 or more cylinders, right? And filter out everything else. That is a very natural interaction. And as far as algorithmic support goes, you can choose the dimensions, you can choose the order of the axis so that you have, you know, that you see some interesting patterns. And you can also use clustering and aggregation. And so here is like an example of clustering that's called hierarchical parallel coordinates. And the goal of this approach was to scale up parallel coordinates to large data sets. And the challenge here is overplotting on occlusion. So here is like a simple data set that we can easily see. Here's an overplotted data set, right? And so what they were trying to do is to take this data and run a hierarchical clustering algorithm on it, and then represent the median of the cluster as one thick line, and the spread in the cluster with the shaded areas, right? So you have kind of like the main effect, and the spread is shown by these shaded areas. And because they use the hierarchical clustering, and we'll talk about hierarchical clustering in another lecture, you could actually break this down. You could have like start out with one cluster, and then you could kind of like increase the number of clusters that you want to show. And so here's like an example with one cluster, with 4 clusters, with something like 6 clusters, and then something like 10 clusters, and so on, right? And so what we see, I guess this progression here is interesting. So first we see the spread up here. Then we see, well, it looks like for these dimensions that we have here, they tend to be fairly consistent, right? But here is a lot of variation. And then if we add one more dimension or one more cluster, we see that there's like a cluster of outlier lines that go up here, right? So it's kind of a really cool idea. It hasn't seen like a ton of traction because it's a little bit complicated to do and to interpret, but I think it's a pretty powerful idea. Yes. So yeah, you want to, for example, what you want to do is you want to avoid, let's say you have you have 3 columns that where all values are high and 3 columns where all values are low. You want to avoid that you go high, low, high, low, high, low, high, low, right? You want to have high and then one transition and then low, right? And so you can do this by, analyzing what is the correlation coefficient, for example, between pairs of dimension and then like doing some seriation based on that. So the little brother of parallel coordinates are star plots, right? Star plots, same idea, but instead of having the axis parallel, they all radiate out from one point. And my favorite example of this is whiskey. So this, and you might have seen this, like actually a few Utah beer breweries have this on their cans, right? These flavor profiles, like is it very hoppy? Is it very malty? Is it sour and so on? And the same thing is here. Okay. The same thing is here for whiskeys. And so here's a few different whiskey distilleries, like Artberg, for example, is a very, smoky whiskey, smoky peaty whiskey. And you see that it has this very jagged appearance and like spicy, nutty, malty, fruity, floral body, sweetness, and so on, right? And so all of these have different profiles, right? And you can look them over. And so what do you think? What's the, is this a good idea? Is this a bad idea? Any thoughts compared to parallel coordinates, for example? Yeah. Yes, that I think the last part is super important to me. The distinct traits, yeah. Yes, that's a good point. It's better. It's better at characterizing in like one item, but worse at showing relationships between multiple items. Yeah.
It's easier to overlay different instances.
So that's the tricky part. Can you do that actually, right? And I would make the argument, and I'll show you like this example here. This gets really tricky because especially as I come closer to the origin, it clutters much more, right? And so I would even argue that you probably want to use these star plots more as these profiles of an individual items and use small multiples of it, right? I think then they can work really well. But I don't think they work so well for like visualizing 500 dimensions, right? Or even 50 or 30. You want to say something?
You're going to use star plots, starting from where they're all balanced, all the different categories.
Yeah.
Ratios all the way down.
That's a good idea. I could kind of like, the whiskey example was alphabetical, but I could do something else, right? I could order by one particular dimension or by an overall appearance or something like that, some main effect, right? So there's lots of choices that you can make as a visualization designer here. Yeah. Probably, yeah. So it's like similar idea to the hierarchical parallel coordinates. Principally, yes. I would still worry a little bit about the what happens in the inner regions of the star plot, right? Then it gets very dense and not a lot of space. Yeah. So generally, like great for individual profiles, like for example, details on demand, right? If you have a parallel coordinates plot and you click on one line, showing that one line as a star plot, maybe a cool idea, right? Make your visualization interesting. And I think it's also cool for these kinds of like marketing purposes, right? If you have 4 projects that you want to compare, a star plot gives you their characteristics and it gives you a shape, a recognizable shape, right? That you can compare easily. Yeah, I did mention a little bit about sampling already. So this is here from a paper from 2006 from Ellis and Dix. And essentially they argue for sampling as a way to deal with scalability. Showing a random subset is extremely efficient, right? It's super cheap to calculate a random subset, and they did the study in this paper that it preserves all the relevant patterns, right? So if you sample reasonably, you can show all of the patterns in the large data set. The thing that you have to be a bit careful about is that you should only use it for display purposes, right? So for example, if I apply a filter, you have to be careful not to apply the filter just to the sample data, but you have to apply the filter to the whole data and then draw a fresh sample, right? So that's just like an implementation detail. There's always a little bit of concern that sampling removes outliers, but there are some algorithms. If this is if you have a case where you want to sample, but outliers are a big concern, there are algorithms that are outlier preserving sampling, right? Or there's outlier detection algorithms, so you could make sure that you preserve all of the outliers, but still sample. And the other thing that you can do instead of sampling is filtering. And filtering, as we've seen in the action, is super important. We want to define criteria to remove the data. For example, we could look at minimum variability. So if you, for example, run gene expression experiments with 2 conditions, usually you don't care about everything that stays the same, right? You want a minimum change between the 2 conditions, and you can filter based on that. Or you could have like a series of 1D filters, or you could filter by like just make sure that my biological replicates behave the same, and the ones that don't, just throw them out, and so on. And I think it can be interactive, it can be combined with sampling, and sometimes it might also be useful to let people script their filters, right? Some filters might get very complex, especially, for example, if you also have networks in there. And so that might be also a good idea. And so now we've talked about axis-based techniques in scatter plots and parallel coordinates and star plots. And now we can combine all of this, right? There's no rule that I can't mix this. And this is a paper for Jark van Wyk group, and it's called FLINA, Flexible Linked Axis. And basically, this is a tool that you can use to draw axes and then say either show me points or draw lines between them. And so then you can create these very flexible layout approaches. And so this is a figure from their paper, and all of these things here are different visualization techniques that people previously had published, right? They had said, okay, here's the new idea for a visualization technique. I'll call it a radar chart or a star plot, right? But in the end, they kind of broke it down to, you have axes, and you either draw points somewhere between those axes, even if they're not orthogonal, or you draw connection lines between them, right? And then you can flexibly arrange. A cool idea, and well, I hope this works. But this is like a tool where you can do this yourself, where you can draw these kinds of axes yourself. Don't make me, okay. So let's say I draw one axis here, I draw another axis here, and what you can see here is that I have these points are already shown, and then how does this work? This and this. Now I'm actually showing you well, I've drawn the same axis. So let me, where's the, okay, I'll draw cylinders here. Okay, and now I am I'm asking this here to create a scatter plot, right? And so as I move this, you can see how the scatter plot changes. And if I put this orthogonally to each other with like the snap feature, I have my fairly standard scatter plot, right? And now I could draw, let's say, displacement, and I could put this here, and I could say, draw me a parallel coordinates plot between those 2 axes, right? And so I can construct this like I want, right? I can now, let's say, add another axis here with horsepower and put this in here. And then I ask it to show this relationship between those 2 axes, right? And so I can kind of clobber together whatever I think is a good visualization, right? So this is like actually a pretty cool idea, right? And a good a good implementation for this idea. This I've shown previously a slide, but I haven't shown the video. And this kind of takes this idea to the next level, right? So what the Felina thing did, this is from some colleagues and myself. And what this does here is it takes these axis-based techniques, like for example, here a scatter plot and here a parallel coordinate plot, and then it also integrates this with other representations like a heat map or like a categorical visualization or a histogram that like lets you transition between different dimensions of a data set. And so what you see here is actually like pop charts, like what Rihanna, U2, ABBA, Elton John, the Beatles, and so on. You see this in different continents, in Australia, Europe, North America. And then you see the number of studio albums, when was their first album, when was their career, right? So we are switching now suddenly from album to artist. And then we say the career starters, are they active or inactive? And so on. So we can kind of like, we can say, is it a male group or female? And so we can kind of like keep going, right? We can like build these visualizations up to look at different aspects of a data set. And so this was a really cool thing. The problem with this is constructing this isn't so easy, right? As you just saw earlier, that like I had to fiddle around a little bit with these axes. It's not just like a plot once, but you have to actually like, it's a little bit like using Illustrator, right? It's a little bit sophisticated. Okay, so so far we have talked about mostly numerical data, but there is also other data, parallel, like categorical data, and parallel sets are a good idea for categorical data visualization. So parallel sets build on parallel coordinates to better handle categorical data. Categorical data is discrete. We typically have a small number of different categories, and there is no implied ordering between the attributes. And typically, you want to find relationships between the attributes. And parallel sets is like an interaction-driven technique. And so this is the idea of parallel sets. Maybe it's easier to explain at this live demo. As you can see, it looks a lot like parallel coordinates flipped over, right? But instead of having each data point traced through something, we summarize, and this is the Titanic data set again. Did people survive or did they perish? Were they female or were they male? Were they a child or an adult? Which class were they in, right? And so we break this up. And then here, before the survived ones, we show these kind of like, the breakdown. So what we see that the survived one, like the people that survived, there's like a very thick band that goes down to female sex, and only very few women did actually die on the Titanic, right? But if you were a man, your chances of dying were actually much higher. So it looks like, from this chart, it looks like something of 75% of women survived on the Titanic, whereas maybe only 20% of men survived on the Titanic. And then we can look downstream, right? This keeps kind of getting, like, first we see these simple relationships, and now here we have the survived female candidates that were children, right? And then down here we have the survived female children that were in second class, and so on. And so we can see these relationships. And as you can see, this gets more frizzy down here. You have more of these crossings because we add more categories, right? So that kind of already implies that there's a limited number of categories that you can, or types of categories that you can visualize. But generally, this is like a fairly useful technique for categories. And one thing you can do is you can reorder this as in parallel coordinates. So that's kind of a useful thing to do. Okay, maybe I'll skip over those things here. They're not so important. Let's talk a little bit about tabular grid or matrix-based representations. So like correlation is kind of like between multiple dimensions is kind of nice to show with these axis-based techniques, but tabular or grid or matrix-based representations also have their advantages. So in a tabular representation, you can think of it as a spreadsheet. Like each variable is its own columns, and each item is its own row, and then you use visual encodings to make it scalable. You can use different things to do that. So here's like a combination plot where we have some kind of like heat map at the top and little bar charts. Like here we have, in this case, these are like, this is one experiment, or like the experiments here in the columns, and then we have different, this is genomic data, the genes in the rows, right? And so you see that for this experiment, that particular one was mutated and had a copy number alteration, but had, for example, like low gene expression for that particular gene. Here's another example that does this, and I think I've showed this before. So this is like really like a spreadsheet, right? So you see a combination of text and labels, but then you see also visual representation of these items. And then you would reveal correlations like by sorting, for example, and you can also go into this overview mode. So what we can see here is this is soccer players, and so age and height doesn't seem to be correlated, right? Because there is complete noise in here. So if we sort by height, we get this noise in age as well. Let's see whether we have a correlation between, well, we should see something here that the correlation, the center forward and the winger, well, it's a little bit hard to see, I guess, but yeah. Anyways, so you can kind of like show, you can show data by just taking like a simple spreadsheet approach and showing and filling in the cells with a visual mark. And like you can actually see something very efficiently here. Like I'm showing you a couple of like 1,100 values right now. And I can kind of like navigate over them. I can reveal the details. And then of course, this allows you to do cool things like group by position and then sort by goals. And now we can see quickly what are the center forwards that are the most successful goal getters is Zlatan Ibrahimovic, versus what are the wingers that are the most successful goal getters is Cristiano Ronaldo and Lionel Messi, right? So like, you know, we can do fancy things with this. A cool alternative is something like Birdifier, which is more of like not an exploratory tool, but more of like a tool for creating charts. And so if we jump into this video here.
Tools are organized in groups. Clara first expands the ESP and clicks on each icon adjacent to the first row to mark it as a header row. She does the same for the left row. Then she expands the shapes group in order to turn the made values into shapes. She clicks on the circle icon next to the first row of the table in order to turn its values into black circles and squares. She is satisfied, so she presses the same icon on the next row and drags down until the last row. This instantly turns all table cells into circles and squares. Now Clara wants a more compact table. Each row can be resized independently using the slider placed next to it. Moving the slider to the right increases the row height, while moving it to the left decreases it. It gets all rows to their minimum size by pressing on the topmost slider, drags down until the last row, then drags left to multiply all selected sliders. She does the same for columns. She also zooms in using the provided functionality of the browser. Now she wants to tidy up the table. She drags over all black arrow icons, which immediately rearranges files by visual similarity, which moves similar countries next to each other. She does the same for rules. Now indicators that are similar are close to each other. To better see similarity, she removes the grid by setting all white separators and black separators to their minimum value. Clara continues to format the table to exhibit more patterns and convey a clearer message. This includes inverting the values of the role, the importance of a good pay, to better show its correlation with another one, the household income. She also emphasizes two roles of a specific type by changing their visual encoding, increasing their height and dragging them aside. She encodes women's suffrage view using lines, and household income using a bar chart. You can choose to reorder only a subset of the rows or to reorder all the rows. Now she can already see country groups with Czech Republic in between that she moves away. Finally, Clara adds separators and annotations to emphasize groups.
So, you know, this is probably one of my favorite visualization techniques, right? It's so elegant and how like a lot of the interaction, like that's called cross sets, right? So you have all of these little widgets here, and it would look like you have to change everything individually, but you can just change one and then drag it down, right? That's a really cool idea. And like, I love these tables, and this is exactly what I would want to include in a paper figure, for example, if you have a small data set like this. And I'm like a little bit frustrated that we haven't, that this doesn't exist in any of the tools that we have, right? You can actually use this tool and you can upload a Google spreadsheet data set to that, but you can't do something like this in Excel. And I think that's kind of like a shame, because I think this is just really nice. How like all of these different pieces, also this automatic rearrangement based on visual similarity. So this is a really cool paper, in my opinion. And so it's kind of related to pixel-based displays, but we want to talk a little bit about pixel-based displays in. Oops. So pixel-based displays. And so pixel-based displays are probably the most scalable of all the techniques that we've talked about. Each cell here is a pixel value and decoded in a color or value. The thing is, ordering is critical, right? So compare those two here. This looks like noise, right? But this here looks pretty good. So we see some clusters here appear. And so we need to, pixel-based displays are useless unless you do some proper, what's called seriation, and you can use clustering algorithms, for example, to do that. Sometimes the order is inherent. Sometimes you have to come up with it, right? And you know, here is like the same thing as a heat map versus a scatter plot, and this is much more compact, right? And you can probably see this just as well on the heat map than you can on the scatter plot. Of course, the downside of pixel-based displays is that all of the dimensions have to be of the same type and of the same scale. Otherwise, it gets really tricky. So just to recap, pixel-based displays can also, like, you know, here's like a 3D pie chart, and the similar thing in a heat map is extremely evident, right? But wouldn't be so evident in a 3D bar chart. As I mentioned, you have to have homogeneous data. It's not so great if you use different data types. This is from a paper from 2012 about like brain cancer, and what they're showing us here, like each of these rows is actually a different data type, right? And they're using the same color encoding, as you can see here, for all of those different things. And so that's a little bit problematic, in my opinion. It's kind of like, it's easy to mix it up. It's kind of like, and you also don't see so much pattern. So it doesn't really work so well for heterogeneous data. It might work on a small table like this, but especially if you want to use these heat maps for large data, then you can't really do that. And recall that color mapping has its pitfalls, like especially red-green color mapping. That could be a problem. So you should use these blue-red color scales by default instead of the red-green color scales. Here would be an example of how a blue-red color scale avoids the pitfall of like not being visible to people with red-green weaknesses. And then also remember that color is relative, right? So that's the tricky part about heat maps. So always be a little bit careful about them. But remember, this is the chart, the same chart here where I had the parallel coordinates. There's nothing really visible in the parallel coordinates plot, but we can see patterns here in the heat map, right? This is 500 by 500 items. And clearly we see some patterns. Clearly this is useful. And so they are very, very scalable. Okay. There's the next thing that I wanted to talk about are space filling techniques. So these are non-tabular space filling layouts where we, like, you know, we had the heat map that was like each row is the same thing as each column, but you could also fill space without this strict row and column relationship. And the one way to do this was what we talked about in this tree maps, the Hive example, where we had looked at these London properties. We've talked about this before, so I'm not going to explain this again. There's also this idea of dense pixel displays, where you can represent each data item or each attribute in an item as a single pixel, and you can fit as many items on the screen as there are pixels. This relies heavily on color coding, but then the challenge is, what's the layout? And so people have tried this with different layouts. For example, like spiral layouts or Hilbert curves or anything like that. And the goal here was to visualize the relevance of set of items which satisfy a query and plot the data in a spiral pattern order by relevance. And so they have these like little 6x6 grids with 6 dimensions, and then they lay these 6x6 grids out in a spiral. That's what it looks like. I'll let you look at it for a moment. Tell me whether you can read something. It's a cool idea, but I don't think it works so well, especially with these very, I don't know. It's just really hard to pinpoint what is going on, right? Okay, so yeah, I have an activity here, but maybe let's just move this to the beginning of next lecture. This is going to take at least 15 minutes, and let's close a little bit early today, and we'll continue with ranking then. Thanks, everybody. And get those desserts.